We're going to look at the second part of 16E, which is all about the polar trigonometric form, or a different way to write complex numbers. So we can convert complex numbers from their Cartesian form into what is called polar trig form. And we do this by using the modulus and the principal argument to represent complex numbers in a different way. So if we have the Cartesian complex number, z equals a plus bi, the one that we're used to, we can actually write this as z equals the modulus of z times cos of theta plus I sine of theta, where the modulus of z we know is the distance of the point from the origin, and our theta is the argument. Just remember, because we're looking using the principal argument, your theta must be between minus pi and pi radians. To convert from Cartesian to polar trig form, first you draw the point, you find the modulus, you find the argument, and you just sub it in to the polar trigonometric form equation. If you're doing the opposite and you're taking a polar trig form and you want to convert it into a Cartesian form, all you do is simply evaluate the trig functions and multiply and expand and simplify. Okay, let's have a look at what I mean. So we've got to show that you can, for the first question, actually write z equals a plus bi in the form that z equals the modulus of z times cos of the argument plus I sine of the same argument. Let's just draw in our Cartesian complex number a plus bi. I'm just going to let this be an arbitrary point here. We know that a is the distance across the real axis and b is the height of the imaginary axis of this point. I'm just going to create a little triangle here. So we know the modulus is that length, the argument is the angle, and then because I can create a right angled triangle here from the origin to z down to a, we can say that cos theta is equal to adjacent over hypotenuse. We can similarly say that sine theta is going to be opposite, so b over, again, the modulus of z. Okay, I can rearrange both of these. For a, I'll get modulus of z cos theta, and for b, I'll get modulus of z sine theta. So all I have to do is sub these two values into my Cartesian equation. If I let a be the modulus of z cos theta and b be the modulus of z sine theta, I'll end up with that z is equal to the modulus of z cos theta plus the modulus of z sine theta times I. This looks pretty similar to my polar trig form, except I'm going to take the modulus of z out the front of both of these trig functions. I'm also going to take the I just to the in front of the sine function, and then we end up with my polar trigonometric equation. So both of these equations would represent the same complex number. Example. So for this example, we're going to take the Cartesian equation 2 root 3 plus 2i, and we're going to change it into a polar trigonometric form. So something like the modulus of z, all in brackets, times cos theta plus I sine theta. So the two things you need to find are the modulus and then also the principal argument theta. So first, let's sketch this point. I'm in the first quadrant because both my a and b are positive. And then we recall how to find the modulus. sometimes called r. So remember, the modulus will equal the square root of a squared plus b squared. A is just 2 root 3 and b is just 2. And just always be wary that r is the same thing as the symbol for that, which looks like the absolute value of z. Okay, when I do this, okay, I'll get the square root of 16. And we always take the positive value for r, and this is just 4 when we're dealing with complex numbers. Now let's find theta. I'm going to use tan to do this. So remember that tan of theta would be opposite over adjacent, or 2 over 2 root 3. We can simplify this a little bit, so we get tan theta is equal to 1 on root 3. And you can use the identity triangles that you know. So tan theta equals 1 over root 3, and theta, using my identity triangle, is pi on 6. And it's in quadrant 1, so that's great. And because it's pi on 6, this is also in the domain of the principal argument, so I can leave it as it is. In this way, I can write my Cartesian equation into the polar trig form. Modulus is 4, brackets, cos pi on 6 plus I sine pi on 6. So I just sub my modulus and my argument into the polar trig equation. This part is actually the easiest part. We're going to convert the following from polar trig form to Cartesian form. All you have to do is evaluate the trigonometry in these equations. So really what I want to do is I want to find out what cos minus 2 pi on 3 is, and I want to find out what sine minus 2 pi on 3 is. Once I know that, the rest is simple. So cos of minus 2 pi on 3, remember that this will be in quadrant 3. Remember, I'm going the opposite direction and 2/3 pi around. In Q3, cos is negative, only tan is positive. So I'm going to get a negative value for cos minus 2 pi on 3. Once I know it's negative, all I have to do is evaluate cos of pi on 3. And again, using my identity triangle or just memorization of this, we should know that cos pi on 3 is equal to a half. Therefore, I can conclude that cos negative 2 pi on 3 is minus a half. Let's do the same with sine of negative 2 pi on 3. Okay, again, I already know this is going to be in the third quadrant, and sine is negative in the third quadrant. If I evaluate sine, so I have sine pi on 3 equals root 3 on 2, but I'll have sine minus 2 pi on 3 is equal to negative root 3 on 2. All you have to do is then take these values and substitute them into your polar trig form of z, and then simplify. So we'll get 2 times cos of my angle was minus a half, plus I sine of my angle was minus root 3 over 2. Okay, then I can see that 2's are going to cancel out if I take them out as a common factor, and I'll end up with z equals minus 1 minus root 3 I. And this was lesson 5. It's still part of 16